Okay, so let's continue the course on Latinger liquids, and this will rebound very well with what Jean-Sébastien, I think I'll move this a little bit away from my mouth, on what Jean-Sébastien told you. In this course, you learn that one can use field theory to get asymptotic behavior, like power laws, the decay at long distance, large time. But as Jean-Sébastien told you, of course, and as I told you also in the course, there are prefactors which depends on an ultraviolet cutoff and which are, of course, totally unknown in the field theory. And therefore, you sort of have some of the informations, but not all of the informations. And now, a priori, if you want the rest of this information, you should find an exact solution of the model, like the one provided by Bethe-Ansatz, and then you can compute the full correlation functions, not only the asymptotics or not only the power law, but with an unknown prefactor and so on and so forth. So what I would like to tell you in this lecture is first that one has learned how to cheat with the field theory as well, so how to push the field theory beyond what it's normally willing to give you and extract semi-exact solution as well. And this is, of course, using the power of other methods like Bethe-Ansatz or numerics. So today I would like to tell you about how we can build quantitative solutions for Tomonaga-Luttinger liquids. And of course, this has only a meaning to build a quantitative solution if you know your microscopic Hamiltonian very well. Otherwise, if you don't know it very well, you're much better off with a field theory, because at the end, you know, you will use parameters which have no physical meaning. For example, if you think about a solid, the fact that we use the Hubbard model, which is a model in which the interaction is only a local interaction, is a caricature of a solid where the interaction is a screened Coulomb interaction, the screening will depend on the energy, and so on and so forth. So replacing the real microscopic model by something where you say, I have only one parameter U, which is the contact interaction, is at best a caricature. It's a caricature from which you can learn physics, you can understand the major process, but you shouldn't expect any form of quantitative agreement with any experiment. But there are systems for which we know in condensed matter. So I showed you cold atoms. In cold atoms, you know the microscopic Hamiltonian very well. The atoms are neutral, the interaction is short range, so contact interaction are usually well implemented and so on. So cold atoms have been fantastic playground to give you experimental realization where you could say this is an excellent realization of the Hubbard model, or this is an excellent realization of the Heisenberg model, or blah, blah. But in condensed matter, a priori for metals, we are a little bit, naked. But there is a category of system, and Jean-Sébastien already showed you, for which we are not defenseless, and that's the magnetic insulators. If you have an insulator, then charge is out of the picture. Particles are localized, like you are here. And the only residual interaction is via superexchange, is via magnetic interactions. But these excitations are not direct magnetic interaction, which is complicated, which is a dipolar interaction. Dipolar interaction in a solid is ridiculously low, and everything is a compromise between kinetic energy and interaction. But at the end of the day, one is usually left with very simple exchange path, like nearest neighbor J, or things like this. So very often, this microscopic Hamiltonian of magnetic insulator is known and measured directly by neutron scattering experiments. So you have really no freedom, and you can say that you are in the same situation than cold atoms, where you can really know what Hamiltonian you're talking about, and I'll show you some examples. So, of course, magnetic insulators are an interesting problem in itself. They have a lot of exotic phases. I won't certainly try to exhaust them here. spin liquids, various form of weird excitations, and so on. So people have been studying this field intensively. They cover many materials, many dimensions, many form of exchange, nearest neighbor, next nearest neighbor, plaquette, and so on. And the point that I want to use here for this next 20 minutes is the fact that the microscopic interactions that you get in a magnetic insulator are usually short range, and thus we know very well the microscopic Hamiltonian. So it means that we can use magnetic insulators as quantum simulators, the same way we use cold atoms as quantum simulators. And that's a use that has not been done in the past. People were studying magnets, and that's it. But I think now with the, I would say, culture of quantum simulations, we can go back to magnet and think, how can we use a magnet to quantum simulate, meaning do an experiment where you can read directly the answer of a particular model you love. We can quantum simulate other models. So there is a little bit more if you're interested in this paper we wrote together with, in particular, Corinna Collat and Christian Ruegg. And this is an unusual way of viewing magnets. I can give you an example, which is not the core of what I will tell about Luttinger liquids, but I cannot resist showing you this example. It's hardcore bosons on a lattice. Hardcore boson on a lattice, here is the Hamiltonian that we could write. And as if you remember, I told you last time that hardcore boson on a lattice are a very good mapping to spin 1/2. So this is the S plus S minus term, and this is the nearest neighbor repulsion of the bosons, but this is the SZ term. So this Hamiltonian here, written in language of bosons, is nothing but the XXZ term, where you get S plus S minus for the spin with a coefficient JXY, and another coefficient for the SZ-SZ interaction. The magnetic field is coupled to SZ, so this will act as a chemical potential for the bosons. If you think about people who are trying to do gate voltage and dope thin films with the electric grid and whatever, this is the paradise, because you can put the magnetic field in 1, in 2, in 3 dimensions, while essentially gate voltage is restricted to two-dimensional films, two-dimensional systems. Otherwise, you don't have the penetration of the magnetic field. So you have a system where you can say, I throw bosons on the lattice, hardcore bosons on the lattice. They have their kinetic energy. They have their nearest neighbor repulsion. And I control their density at will by controlling the magnetic field. And I can go from 0 boson per side to 1 boson per side. So I can go from an empty band to a field band, which is a rate of doping, which again are way beyond the 10% that you can reach in this type of systems. You have probes. The probes are magnetization. It gives you the number of bosons. You have the neutrons, or the NMR, which is measuring the dynamical correlation function, and you heard this in the talk of Jean-Sébastien. And the SZ-SZ correlation function for the spins is the density correlation of the bosons. So this is direct measure of the structure factor of the bosons, while the S plus S minus correlation, which is also measured by neutron scattering, as Jean-Sébastien explained to you, is measuring psi dagger psi. So this is measuring the single particle Green's function for the bosons. It's measuring the G1 for people who like this denomination, while this is the G2 correlation. So by simply doing a neutron experiment on the spins, you get access to both correlation functions at the same time. So let me show you a little example, which actually we discovered with Alexei Zvelik in the last century, just 2 years before, okay? And that's a very simple example of a material which will be paved by dimers. So imagine that I have a system where this yellow bond is much larger than all the other exchange. of course, then I can first diagonalize this two-spin problem, and you know that two-spin one-half coupled by antiferromagnetic exchange, they can be in a singlet state or in a triplet state, so it's very easy. The eigenvalues are the singlet state as the lowest energy, and I have the degenerate three states of the triplet state, which can be either with Sz equal 1, Sz equal -1, or Sz equal 0, which is a quantum superposition of up, down, and down, up. And the singlet is the other quantum superposition. Now, if I put a magnetic field and I completely ignore the white bonds, then the magnetic field will simply lower the lowest triplet. So I will have at some point, for the spin, it means that the spins sort of go up. They go in the direction of the magnetic field. And then I will get a quantum phase transition when this triplet will become the ground state. So I go from a system with 0 magnetization per rung to a system with magnetization 1 per rung. Okay, that's a kind of boring quantum phase transition, but it's a quantum phase transition. Now, what happens if so I can use the same mapping. I can say the singlet is 0 boson, the triplet plus is 1 boson, so I can view this system as either putting a boson here on the rung or not putting a boson on the rung. So 0 boson here, 1 boson here, 0 here, 0 here, 1 here, and so on. And now, if I put the white exchange, it's easy to see that the only thing it can do is to make this triplet hop to the next rung. So essentially, what will happen because of the white bonds, so another smaller exchange, is that the triplet will hop. So my boson have kinetic energy, and they will delocalize on the lattice, which means that this level acquires a certain width, which is the bandwidth caused by this exchange. So now, instead of having a single phase transition, I will have 2 phase transitions when the first level of the triplet is reaching the bottom of the band. So when my magnetic field is reaching, I start filling the triplets. I continue filling the triplets until I've put 1 triplet per rung. So I will get a magnetization curve that will do something like this, where this is 1, this is 0, and now I have 2 critical fields, Hc1 and Hc2, which corresponds to the bottom of the band and the top of the band. And you can check, you have bosons. They are super diluted here, so their interaction don't matter. Even if they are hardcore, they don't matter. So what do you get here? You get Bose-Einstein condensation. So this system is a perfect system to realize Bose-Einstein condensation. The same Bose-Einstein condensate you can realize in cold atoms, you realize with this system of dimers. Now you could say, what is the phase? What is well, the system is now in a triplet, but the spins are projected in the plane, in the xy plane. They have an angle. So if you look at the angle that the spins are doing in the xy plane, this is characterized by an angle theta. And this can be incoherent from side to side, or they can all lock and go together from side to side. The phase where they are incoherently ordered in the xy plane from side to side, this is the normal phase. And the phase where they are all locked in the same direction, this is the BEC phase. So you can, for example, measure the staggered magnetization along X or along Y to know if you have a Bose-Einstein condensate or not. And there is a very nice mapping. If you want to know more, I refer you to this little review we wrote with Christian Ruegg and Oleg Chernyshov. But this is a kind of cute realization, and this can be tested experimentally. I won't go, but there is a compound which is called thallium copper chloride where people saw this kind of thing. So this is very unusual for condensed matter, but we can use condensed matter as a very controlled realization, but at the price of dealing with insulators instead of dealing with metals. Okay, so this pushes the theorist, because now we have something for which we know the microscopic Hamiltonian or whatever, I go back now to my Luttinger liquids to say, can we give an exact solution? Can we do as well as Jean-Sébastien with a better ansatz, but for models which are not better ansatz solvable? And the answer is yes, we can. Someone said that before. Yes, we can. And of course, we have to cheat a little bit. And so I will explain you how we cheat. And the way to cheat is to use two techniques. And to get the best of both worlds by using each technique when they are efficient. So field theory is asymptotically very good. It's good when the distance is larger than the lattice spacing, the time larger than the microscopic time, the temperature much smaller than the largest energy scale in the problem, which let's say the magnetic exchange or something like this. But of course, the price, as we discussed, is that the amplitudes and the TLL parameters are unknown. So when I write something like, I don't know, S plus, S minus of R is A times alpha over R to power whatever, 1 over 2K. I don't know what is K, and I don't know what is this combination here. But I know potentially it's a power law, and I know which mode is a power law. Now we could turn to numeric, or we can turn to better ansatz. If we turn to numerics, then numerics, whatever is your favorite technique, whether it's exact diagonalization, Monte Carlo, Giamarchi, whatever, is very efficient at short time and short distance. By definition, you work on a small system, can be 16 sites or 20 sites if you do exact diagonalization, up to 40 if you do spins. It can be 100 to 200 if you do the MRG, and so on and so forth. But anyway, it's efficient at short time, short distance. But the numerics take into account the full microscopic model. You give yourself the Heisenberg model, the Hubbard model, the whatever, and then you compute with this. And so the idea is to combine the numerics or the better ansatz for models for which better ansatz solution exists, and the field theory, and use the numerics to determine this coefficient. Don't think there is color. No, so we'll do, yes. So we'll do without color. So you use the numerics to extract simply this. This is coming from numerics or better ansatz. And this is coming from numerics or better ansatz. And then you can do this at a very small cost in the numerics or moderate cost in the better ansatz. And then you inject these parameters in your field theory, and your field theory becomes essentially exact. When I say exact, it means it will become quantitatively efficient beyond 2 or 3 lattice spacing. So let me show you how it works. And for that, let me take an example, which is an organic ladder, because it's a 1D system, so we can hope to use Tomonaga-Luttinger liquid. So here is a compound. It exists. It's not an artistic view, which has copper side here, which carries spin 1/2. The magnetic exchange here is about 12 Kelvin in this direction, and about 3 Kelvin in this direction, just for fixing the thing. And the system is organizing in this 3D structure, but the exchange between the ladders is very weak. The J prime here is about 50 millikelvin, so there is a huge range of temperature where you can really consider that this is made of independent 1D structures. So this problem is not better ansatz solvable. It's a ladder. It can be mapped on a spin chain in a certain limit, but I won't discuss this right now. But we thus have to use the numerics to say something. And the idea is what I just said, compute numerically using, in our case, the DMRG technique, the non-universal parameters, the exponent and the amplitudes from the microscopic Hamiltonian, Gesundheit. And here is the result that we get. It doesn't matter precisely. K is the Luttinger parameter. The other curve is the velocity u. And just look at the red curve. Let me ignore the green curve for the moment. And this is as a function of the magnetic field. So this is between Hc1 and Hc2. This is exactly the graph that I did before. This material has zero magnetization. Then it starts to get magnetized. Then here it's saturated. So between Hc1 and Hc2, this material has a partly filled band of triplets. But of course, they are interacting. So between Hc1 and Hc2, this is a Tomonaga Oettinger liquid. So we have to describe it as a Tomonaga Oettinger liquid. So if you want, I could sort of write a temperature magnetic field phase diagram. I have Hc1 here. I have Hc2 here. Here I have a gap which closes. Here I have a gap that opens. And now I have a coherent scale here. It's not a phase, it's just a transition, which corresponds to roughly the maximum energy. So this is roughly the distance to the bottom of the band, which is roughly proportional to J parallel. And again, my system is made of a very strong J perp here and a weak J parallel. And I can describe this system. Okay, so this is of order J perp. This is of order J perp. And this is of order J parallel. Okay, below this temperature, I have my excitations, and this is a Tomonaga Oettinger liquid. Okay, so how can we describe this thing? Well, now we inject in the theory, and let me give you an example, which is the nuclear relaxation time, the so-called 1/T1 in NMR. And here is the field theory formula. These are d gamma function, so this is product of gamma function. So we know everything in this formula is characterized, except usually we don't know the velocity, we don't know the exponent, and we don't know the amplitudes here. But thanks to the little trick of computing things from the numerics, so not only the exponent, but also the amplitudes, we now have everything in this formula that we need to know. The only thing we miss, but our colleagues, experimentalists, give it to us, is the hyperfine coupling, which couples the nuclear spin to the electronic spin, and they know it within 10–20%. So this is, but this is one number. And now we can try to fit the whole magnetic field dependence of the 1/T1 with maybe one number as an adjustable parameter, and again, known within 10–20%. So this is what we did in this paper. The experiments were done, Martin Klamsek did the experiment in the group of the late Claude Berthier in Grenoble, and we helped with the theory, Pierre Bouillot and Corinna Collat. And here is the result. So the dots are the experimental points, and this is about 7 Tesla, this is about 12 Tesla. And essentially, the red curve is the curve, the function that I showed you before, where there is no adjustable parameter. Everything has been determined from the numerics out of the parameters of the Hamiltonian that we know very well. We know what are the exchange constants here in this material. And you see that the agreement is perfect. There is no other word for it. Okay, maybe not perfect, but at least very satisfactory. We reproduce not only the shape of the curve, but we also reproduce the amplitude of the curve. So now, I would say in 1D, we will be in a situation where we can not only give qualitatively power laws or whatever, but we can, combining not with a single technique, but combining either Bethe-Ansatz and field theory or numerics and field theory, we can essentially reach places which would be very difficult to reach with one technique alone. The 1/T1 is exceedingly difficult to compute if you want to compute it brute force from the numerics. Now we know how to do, but this is very difficult. Here is another example how these materials can be used as quantum simulator of Oettinger liquid. This is an experiment done in the group of Andrei Zeludev in ETH, where they measured by neutrons the single particle correlation of the bosons, for which we know the Luttinger liquid form. This is on another ladder material, which is called DIMP, which has about the inverse coupling. This is about 12 coupling, and this 12 Kelvin, and this is about 3 Kelvin. And by measuring the neutron spectrum, you saw these figures in Jean-Sébastien's talk. This is the energy, this is the momentum, and the intensity. Of course, the color code tells you the intensity of the response. They can plot the intensity of the response. We know the field theory, so we know what are the good scaling parameters, and what needs to be plotted is the structure factor divided by the temperature to some power, which is dependent on the Luttinger liquid exponent, and this should be plotted as a function of omega divided by the temperature, which is the good scaling for a Tomonaga Luttinger liquid. This is a conformal field theory with Z equal 1. And then, essentially, you see the data from the neutrons, and the black curve is the Tomonaga Luttinger liquid curve. So this is a very good, I would say, and satisfactory situation where we can say that now we are in control and we can push the experimentalists in their latest trenches, I would say. Now, this is all good and nice, but what happens if I am here? If I am at a temperature which is larger than the largest energy scale, then I cannot use field theory. And as Jean-Sébastien told you, then you need another method to compute the correlations. The methods, then, there is only Bethe-Ansatz, or if the model is not exactly solvable, numerics. And fortunately, the DMRG, when I use DMRG, I use it in a loose sense. This is matrix product state, and you will hear about it, I'm sure, in another lecture, can be used now to compute dynamical correlation functions. That was the big progress that was accomplished around 2005 compared to the first implementation of the method by Steve White in 1990. Now, not only the static correlation can be computed, but the dynamical correlation can be computed. So here is an already ancient calculation where the scattering, the neutron scattering correlation, so again, frequency, momentum, and the color code gives you the intensity of the response, has been computed for the ladder that I showed you. You see the three structures that correspond to the three triplets. So you see the excitation from the singlet to the lowest triplet, middle triplet, higher triplet. And we can very well compute everything here from the DMRG down to energy scales which are typically J over 20. Don't take this too seriously, but this is the omega mean that we can reach, and that will always be in this ballpark. 1/10, 1/20 of the, then we hit an exponential wall and the calculation is not controlled. So the field theory is good. So this is 1 here on this scale. And the field theory will be taking over and will give you the answer here. So you see now we are in a very satisfactory situation, because if I look as a function of the energy, we can go down here with the numerics, and then the field theory, which is sort of taking over below J, is giving you the rest. And that's how we can cover the whole spectrum. So here is the brute force numerical calculation, and if you do a slice, you can compare with the neutron scattering experiment, and this is a very good agreement. The other curve for information that is on the graph is the mapping of the ladder to a spin chain, and then using Jean-Sébastien's Bethe-Ansatz solution to study. You see that this is also an excellent agreement. So the mapping of the ladder for this particular compound to the chain is reasonably accurate and can be used. And then you use the power of Bethe-Ansatz to get directly the correlation function without needing numerics. Okay, here is a more recent calculation, which we did with Noam Questin. And just to show you that now not only one can compute this correlation out of the numerics at finite time, so finite frequency and finite momentum, but also at finite temperature. This is calculated for increasing temperatures, going from smaller than J to larger than J, and of course you see the blurring of the response as the temperature is getting stronger. What is interesting is here a comparison for one of the mode at Q equal pi of the numerics with the field theory, and you see that the blue points are the numerical points, and the red curve is the prediction of the field theory with the exact exponent injected from the numerics. And you see that the field theory is working very well where you would expect it to work. As long as the frequency is smaller than J, the agreement is very, very nice. Of course, if you go at larger frequencies than J, the two are getting completely different, but again, here you recover a very nice agreement. And now if you go to too large temperature, you see that you completely screw up the response, because the field theory has no reason to work when the temperature is larger than J itself. So this study show you that now we have a sort of good mix between the numerical studies and the field theory studies, which can be much more efficient, again, at very small energy scale. So you could say, oh, that's great. So what? What is the use of this? Well, that's useful to have such solutions. For example, here is a compound that was synthesized in the group of Andrei Zeludev already 10 years ago. And they knew it was a ladder, but they didn't know the parameters in the Hamiltonian. So how do you determine the parameters in the Hamiltonian? So either you can do direct neutron scattering, but it was difficult to do neutron scattering at the fields, at the magnetic fields which were needed for this compound. This is the ladder I already showed you, DIMP. Okay, now we know it's about 12 Kelvin, and this is about 3 Kelvin. But at the time, they didn't know. So what did we do? We run numerical calculations of the correlations, and we compare with their zero field neutron scattering experiment until we got a match. And that gives us the parameter we have to put in the Hamiltonian. And because we know we make essentially no mistake going from the Hamiltonian to the correlations, that's ab initio reconstruction of Hamiltonian. By the way, here the points are the experiment and the full curves are the numerics. Don't get fooled. We are much better than them. They just get these points here. And we have the full spectrum. So we fit the spectrum, you see, that's very easy to check. And now we tell them, oh, 12 Kelvin, 3 Kelvin. And this is something they can do, can check, because now we take this Hamiltonian and we compute the fact that this compound has a three-dimensional phase transition. I don't want to go too much in the detail on how we compute this. But using the Hamiltonian we had just determined, we determine here this red line, which is the transition towards a 3D ordered state. And here are independent measurement of specific heat, which signal the transition. You see the agreement is again excellent. So this is something where we can really determine Hamiltonians, reconstructing them from the measure of the correlation function. And I find this a very, very satisfactory situation. Another thing that one can, for example, compute with this type of methods, and this will be the last example I will show. Remember that I told you, oh, if we are not in 1D, but if we are in 3D, this deconfinement of the excitations will not work because of the presence of the other chain. This gives you a string whose energy is growing as the distance between the excitation. I showed it to you for the spin-on and the hole-on, but it's also there for two spin-ons in a magnetic insulator. Actually, I lied a little bit. It's not that I lied, but you have two particles which are linked together by a potential. What should you get? It's like the hydrogen atom. you get resonance at discrete energy levels because you get bound states. Okay, here the potential is not 1 over r, it's a linearly confining potential. Something, the potential V is growing with a distance. But fortunately, this has been solved, and this is expressed in terms of Airy functions and whatever, so you can find it, I think, in the Morse and Feshbach book. So we have bound states. So we should see this bound state. Here is the calculation of the correlation functions of spin-spin, and you see the bound state. You see the resonance here in the neutron spectrum, which tells you every time you pass one of these highlights here, it means that you are crossing the energy of spin-on bound state. There is a compound, Bakovo, which is a good realization of a 1D chain. And lo and behold, here is the spectrum we can compute. This is computed from the MRG. This is a slice here at a given momentum. And this is the comparison with the experiment. So this is showing you that we get an extraordinarily now fine control on the correlations that we have in the system. Okay, so let me stop here, because in a way, I would like to give you a take-home message with that now we have good theoretical methods to deal with cases of what I would call simple equilibrium 1D systems. And this is analytics, and this is numerics. The analytics is both field theory and Bethe-Ansatz, and numerics is mostly the MRG. But combining this, we can really understand very well simple 1D systems. Now, this is a stepping stone to go beyond. So this is understood. Now we are, for these problems, we are back to engineering. It's not research anymore. We understand what is going on. But now we are in the same situation than having the Fermi liquid in the 60s. We can study what happens if you put a perturbation. What happens if you put a small attraction? Superconductivity occurs. What happens if you look at distortion of the lattice? Charge density wave occurs, and so on. So now we can do the same thing in 1D, building on the Tomonaga-Luttinger liquids. And of course, the problems there are far from being resolved. And I will try to show you in the, 30 minutes that I'm left, 37 minutes that I'm left, a couple of examples which are kind of intermediate. These are examples going beyond simple Luttinger liquids, but we still reasonably understand them. And the last lecture, we keep it for real nasty problems and things where there are difficulties. And most importantly, there are very controlled experimental realizations, both in condensed matter and in cold atoms of Tomonaga-Luttinger liquids. So, again, we have quantitative agreement. Yay! Is it the end of the story? Should we all go home and work on 3D materials or 2D materials? And the answer is, of course, no. As I said, we are now at the beginning of really studying perturbations on the Luttinger liquid. So we need to go, of course, beyond Luttinger liquids, but we build on the Luttinger liquid. Okay, so let me take a couple of examples, and today I will deal with what I would call 1D additional perturbations. So I'll add a little bit of complications. It's not multi-component, but it will be multi-chain that I will show you. You can put a lattice on the chain, and then you know you can cause Mott transitions and so on, and I will show you also the case of disorder. What happens if you put disorder on a 1D system. So let me start first by a funny question that we looked at a long time ago with Edmond Rignac, which is what happens if we take two bosonic chains. So a ladder of bosons. So in a way, it's not very far from the ladder of spins that I showed you here. And the question we wanted to ask ourselves, I know that if I have a 2D superconductor, I have a Meissner phase, where I have currents at the edge, and then I have a bulk phase, if I continue to increase the field, where I will have vortices. So do I have something similar in 1D? Do I have a transition between a Meissner phase and a vortex, an Abrikosov vortex phase, if I put a magnetic field which is perpendicular here to the two chains? That's the simplest we can do. 3, 4, 5, 6, infinity, you go back to 2D. So I have one bosonic chain here, so I have H1, I have H2, these are interacting bosons, and then I put tunneling minus T perp, psi dagger 1, psi 2 at the same point, so I have to integrate over dx. And this I want to solve, and of course I have magnetic field plus magnetic field. Okay, so here is the situation. Now here is the Hamiltonian. You see you can put the field as a gauge field either in the longitudinal hopping, or you can put it as a gauge field on the transverse hopping, as long as the circulation of the gauge field on the plaquette is giving you the flux, is giving you the magnetic field. You choose your vector potential the way you want. That's gauge invariance of the theory. And of course, you put an interaction in each one of the chain. Let's ignore the interaction between the chain. It's not important for what I'm going to say. And if I bosonize, so if I use the bosonization method that I explained to you, I can introduce two fields, phi 1 and phi 2, but I can do the symmetric phi 1 plus phi 2 over square root of 2, and the anti-symmetric, which is phi 1 minus phi 2 over square root of 2 combinations. And the Hamiltonian takes a very nice shape, which is, again, let's forget about this, doesn't matter, that I get a quadratic Hamiltonian for the symmetric component, I get a quadratic Hamiltonian for the anti-symmetric component, and the coupling between the chains is locking the anti-symmetric component to the minima of a cosine. This is just saying that, same thing of course for the theta, it's just saying that I want the phase theta 1 to be the same than the phase theta 2. That's just ordering of the bosons on 2D systems, okay? So here is the Hamiltonian, and now the gauge field, which is coming from the magnetic field, is acting as a shift of this cosine. And this is a very nice Hamiltonian that has been studied in the past, which is called the Pokrovsky-Talapov Hamiltonian, when people were studying incommensurate phase transition on adsorbed gases on the surface of material. And we know how to solve this Hamiltonian. And lo and behold, what we find is that there are two phases. At low magnetic field, there is a phase where currents are circulating on the legs here in opposite direction. So if it was separated, you would think of it as a Meissner phase, where you get only current at the edge of the system. And then, if you exceed a certain threshold of magnetic field, you start having currents which are also circulating on the rungs. And this is like vortex phase. So this is like creating vortices where you get current which is circulating like this, and of course giving you a vortex. And the density of such vortex depends on the magnetic field. So this is a very nice analog of type 2 superconductor, where at small field you get a total expulsion of the flux, and then when you increase the magnetic field, you get penetration of the flux as a function of vortices. So you could sort of visualize this. If you look at the quote, not magnetization, but the current, you find that you get perfect screening of the external magnetic field, and then you get penetration. And if you have read the TINCAM or any book on type 2 superconductivity, you will remember this curve as the magnetization curve of a type 2 superconductor. So at the time, we were thinking of Josephson junction arrays or other systems like this in which to test this, because this was before cold atoms. But actually, people came with this in cold atoms, and this is a paper coming from the group of Monika Edelsberger and Immanuel Bloch in Munich, where they did realize these bosonic ladders. They did put an artificial gauge field. Again, atoms are neutral, so it cannot be a real magnetic field, but they know how to mimic a magnetic field by Raman pulses. And lo and behold, they saw here the change of current that occurs at the critical value of their, let's say, magnetic field, and they observe this vortex phase and this Meissner phase. The reason why I'm showing this, first is to show off, clearly, but the second reason is because you see that now we have to deal with Hamiltonians which are a little bit more complicated than just quadratic Hamiltonians. We have to deal with an Hamiltonian which is HA, which is quadratic, but then we have something like minus T perp cosine, whatever, square root of 2 theta A, integrated over dx. And this type of Hamiltonians are more complicated to solve. This is known as the Sine-Gordon Hamiltonian. But, okay, we have to deal with them because this is the type of Hamiltonian that will naturally occur when we start complicating the problem. You also see that building on Luttinger liquid theory, we can describe phases which are gapped, which are not necessarily Luttinger liquid ones, by simply using the dictionary and re-expressing things in terms of the new variables, phi and theta. A very similar effect occurs if I put a lattice on a chain, and this is the phenomenon of Mott transition. So you know that if you have repulsive particles and you put one particle per site on a lattice, then you get an egg box with the fact that if these particles, okay, here it's particle with spins, green and red are spin up and spin down, but if a particle goes to this site, it will feel the repulsion, and therefore the kinetic energy is not enough to make it move, and you get a nice insulator. And this is an insulator which is driven by repulsion. If I switch off the repulsion, nothing prevents this guy from jumping here, jumping there, and starting to move, and I recover a metal. So this is the famous Mott insulator, for which Sir Neville Mott got the Nobel Prize. And we know that this occurs at special filling, one particle per site, and so on and so forth. So can we describe this kind of phenomenon with Tomonaga-Luttinger liquid? Yes. We, again, use the same dictionary. We have our bosons, for example, in the continuum, can do the same thing for fermions. Now we add a periodic potential which coupled to the density, and we know the density as these oscillating terms. Remember, 2 pi rho 0 and whatever. So when 2 pi rho 0 will meet the period of the periodic potential, this will not oscillate, and this term will stay in the Hamiltonian, and will give you something which is simply a cosine. So if the periodic potential doesn't match the natural period of the bosons, namely if you don't get a boson per site, per oscillation of the potential, then you get this kind of cosine, which has here a term which is growing as x, and this makes the cosine vanish. This shift scrambles enough the cosine to make it vanish. So you're in the incommensurate phase, you're in the superfluid phase. You can erase this term from the Hamiltonian. You get the quadratic only, so this is a Tomonaga-Luttinger liquid with superfluid. But if you are matching the period, so if 2 pi rho 0 is equal to q, then you get this term in addition to the quadratic term. So you see that now you will have to deal with an Hamiltonian, which is something like, let me write an action. S equal 1 over 2 pi k, integral over dx d tau of d tau phi square plus dx phi square. This is the momentum. This is p square over 2m is 1/2 of mv square. V is the time derivative of phi. Plus or minus g cosine 2 phi of x and tau, integrated over x and tau. So now you see exactly what happens. It's not a Latinger liquid anymore. This would just be the Tomonaga Latinger liquid. But now, yeah, there are two terms which compete. This term is very happy to let phi fluctuate. And when phi fluctuate, this is how you get these power laws and whatever. This term is not happy at all to let phi fluctuate. It wants phi locked into what minimizes the cosine. 0, 2 pi, 4 pi, 6 pi, and that's it. So if the cosine wins, phi is locked. It becomes a number. It becomes a classical variable. Then the density is perfectly fixed. It becomes a number. That's the Mott insulator. If, on the contrary, this term loses, it's erased from the Hamiltonian, and then I get the superfluid. So we can describe the Mott transition by studying the quantum phase transition that occurs in this Sine-Gordon model, which, by the way, is also an integrable model, so which can also be studied by Bethe-Ansatz. And there are other methods to study this model. I won't go into details on how you can study it, but I'll just point to mapping. And by understanding the nature of the phase transitions in this model, we can understand how you go from a superfluid to a Mott insulator in one dimension. If you want an image in space and time, time would be this direction, you have a phi, which is kind of wiggling in a potential created by the cosine, and either it stays in the minima of the cosine, in which case this means that phi is locked here, and you get one boson per site in real space, and you get the insulator, or phi is able to wiggle from one minimum to the next, and then your bosons are delocalized, and they can go everywhere. This transition is well known. Actually, it's not totally obvious, but it's the Berezinski-Kostelis-Thouless transition, for which unfortunately Berezinski passed away, but for which Kostelis and Thouless got the Nobel Prize not so long ago, and which also described the two-dimensional XY model in presence of vortices. So this is a very interesting connection that actually the Mott transition in one dimension from a superfluid to Mott transition is exactly an implementation, the quantum version, of the Berezinski-Kostelis-Thouless transition, which has been invented to solve classical two-dimensional models. Okay? Here are the three heroes of the BKT transition, which was invented for the 2D classical XY model. So this is a model where spins are only described by one phase, and the interaction is just cosine theta I minus theta j. And of course, the point is that if you are naive and you say, I expand the cosine, saying theta I and theta j have to be close, then you get only the power laws. But what these three gentlemen realized is that you should worry about this phase forming vortices. So you could have configurations where the spins were forming vortices like this, in which case the phase of neighbors is not close to 0, but is looping by a factor 2 pi when you're on the plaquette. By the way, this is also a vortex. Very often you would say people, oh, vortex, anti-vortex. This is also a vortex, because you turn in the same direction. Here you rotate by 2 pi clockwise. Here you rotate by 2 pi clockwise as well. So don't be fooled if you see something like this. This is also a vortex. Okay, so this is a remarkable transition, which is a transition without an order parameter, because both in the low temperature phase and in the high temperature phase, the order is 0. And this is a transition which is characterized by the appearance of this topological excitation. So here is a little drawing where there are vortices and anti-vortices here, which have been put on the picture. Now you could say, what is the link with the quantum version of it? Where do I see vortices? Well, actually, if you remember your quantum mechanics, exponential of IA times the momentum applied to a configuration of position translates the configurations. It's the translation operator in quantum mechanics. Now, if you remember what phi is the gradient of phi is the momentum conjugate to the variable theta, and vice versa. So phi is the integral from minus infinity to x of the momentum conjugate to the variable theta. Fine. So when I apply a cosine of phi to a configuration of theta, what I do is I apply exponential of I 2 pi times the momentum, which means I apply exponential of I 2 pi integral from minus infinity to x of dy pi theta of y, which means I translate theta by 2 pi on all the string here until the endpoint where I am in space and time. Time and space. So actually this object is the object creating a vortex in the variable theta. So you see that the quantum version replaces the second direction by the imaginary time of the quantum Hamiltonian, and the operator cosine 2 phi is an operator which creates some form of vortices which are very compact. This goes from 0 to 2 pi, but you can then confine them a little bit, spread the phase a little bit more by the quadratic fluctuations, and therefore it's exactly mappable to the BKT quantum phase transition. So I could have written my Hamiltonian on the board, could have been written also that way, and in that case you see that this is the operator creating the vortices, and this is like the spin waves of the BKT transition, where K plays the role of 1 over the temperature of the classical problem. If I had a classical problem, this would be beta H, and K would be 1 over beta. So you can really map this problem onto a 2D XY model in presence of vortices. Okay, I don't want to go in more details. So you get phase diagrams that we can compute from the Luttinger liquid theory. For any commensurate filling, you will have one of these cosines staying in the Hamiltonian. So here is the phase diagram for bosons as a function of the repulsion here and as a function of the chemical potential. If I have 1, 2, 3 boson per site, then I am commensurate with a factor 2 here. Then I have certain exponents and certain magic value of the Luttinger parameters at the transition from the superfluid to the Mott insulator. And also, if I dope the Mott insulator, thanks to the Pokrovsky-Talapov transition, we can determine that this occurs for a value of K, which is 1 here. Now, I could be commensurate with 1 particle every 2 sites. Now, you would say, I cannot get a Mott insulator. Depends what you call a Mott insulator. If I have 1 particle every 2 sites, you cannot get an ordered phase with only on-site interactions. But you can easily get an ordered phase if you say that you have also a nearest neighbor repulsion. So this is described by exactly the same Sine-Gordon theory, except because the period is longer here, the coefficient in the cosine is not the same. So again, I don't want to go into details. I don't think it's important. It just shows you that this technology of Luttinger liquid allows you to describe this Mott transition. And here is a comparison between the field theory prediction and Giamarchi calculation that were done by Till Kuhner, Hartmut Monin, and Steve White long time ago, where just to confuse the enemy, their convention for K is exactly the inverse of mine. So when they tell you here K equal 2, K equal 1/2, this means actually K equal 2 for me, so we are in perfect agreement. And when they tell you here K equal 2, it means K equal 1/2 for me, and we are again in perfect agreement. But this is a beautiful, I would say, confirmation that indeed you get these universal values at the tip here of the transition between the superfluid and the Mott insulator. Note that the phase, which is the Mott insulating phase, is extremely narrow here because the gap is exponentially small. So it's a tour de force numeric. It's a numerical tour de force to really determine that the tip is here and not there. You can easily be fooled by thinking that the transition is there and not there. But if you look at the Latinger exponent, you immediately see that there you would be around k equal 2/3, and it's not the right value for the transition. So the field theory helps you there to know where you are in the phase diagram. Now you could say, can one check this? Well, yes, the answer is yes. These are experiments that were done in the group of Hans Christoph Nagel in Innsbruck. And what he did, he took a gas of bosons, and he put a very small periodic potential, and he increased the periodic potential, and he increased the repulsion between the bosons. So this is the lattice depth, is the height of the periodic potential, and this parameter here is the strength of the interaction. This is free bosons, okay, here, let's say, and this is infinitely repulsive bosons. Now, if the potential is very deep, you can say that you reproduce a Hubbard model. If I have a periodic potential which is that deep, then I can consider that the only place where my boson can be are here. And then I've done a system where I jump from side to side. But if the potential is very shallow, I cannot say that I have a Hubbard model, but I have my periodic potential on the top of the Hamiltonian. And what he did, he measured, by measuring the gap, he measured the position of the phase transition. And you see that there is here a critical value of the interaction where any small lattice potential will create the Mott insulator phase, as long as the repulsion between bosons is sufficiently strong. And this is perfectly in phase with this field theory, which tells you that when k is smaller than 2, you're immediately, if you're commensurate, you're immediately in the Mott potential, even if the size of the gap here, if the potential is super small. That's a very important difference between 1D and higher dimension. In higher dimension, if you want a Mott insulator, you need a deep lattice potential. You can take bosons even if they are hardcore, and if you put a very shallow periodic potential, they will not be in the Mott insulating phase. They will stay superfluid. So 1D is able to lock itself immediately as soon as the potential is infinitesimal, provided the repulsion is larger than a certain critical value. So it's a little magic effect. Think about it. It's very non-intuitive. You put a tiny periodic potential, much smaller than the kinetic energy, but because the particles repel themselves enough, they go into an insulating phase. The beauty of divergent susceptibilities. This is a more recent experiment that was done in the group of Giovanni Modugno in Florence, and we help, together with Laurent Sanchez Palencia, for the theory, essentially refining a little bit on the position and the values compared to Hans Christoph experiment. And essentially, you see the same, exactly the same trend, and you see that the experiment is ending exactly where it should be. And to the best of my knowledge, this is the most precise determination, actually, of the critical value of the BKT jump that has been done compared to what has been done directly with two-dimensional systems. That's funny that you need to go to 1D quantum problem to get a good determination of the BKT jump, but this can be done with a very, very good accuracy here. And lo and behold, we are exactly where the field theory tells us that we will be. Okay. Now, something which is a little bit weird. This is a transition where we all understand what is going on in a Mott insulator. It's what you do here. Okay, you're not exactly one per site, but if you were one per site, you would say, oh, a Mott insulator, it's the egg box theory. You know, you put an egg in each one of the minima of the box, and then if they try to move, they can't because there is no space. Yes, but there are also weird orders. And let me show you a weird order. I told you that I have a sine-Gordon Hamiltonian. So I told you that I have minus g cosine whatever, 2 phi. And I want phi to be in one of the minima, like phi is equal to 0, or phi is equal to pi, or whatever. So what is ordered is not just the density. The density is some function of phi. But what is ordered is phi itself. So how can I test that? Well, the density would tell me rho is blah, blah, blah with cosine 2 phi. But if phi is ordered, it means that if I could do a function which is cosine lambda phi with lambda arbitrary, it should still be ordered. It should have an average. How can I do this? Well, answer, you count if you have only local probes. Because if you have only local probes, the only thing you have access to is the density. So you only have access to cosine 2 phi. But if you have a non-local probe, you can remember that the density rho of x is sort of 1 over pi grad phi. So phi is the integral from minus infinity to x of pi times dy times the density rho of y. So you can measure this and check whether this is ordered or not. And that's the beauty with cold atoms. And that's the beauty with this type of order parameters. This goes by the name of string order parameters. These are things that got invented shortly after BKT transition. There are a lot of string order parameters that people tested. This was also invented for Haldane gap phase, where everything seems to decay exponentially, but there is a hidden order parameter, which actually is non-local, which you cannot access by local probes. And here, for the Mott transition, we get essentially a non-local order parameter. So this is something we discussed in this paper. And again, lo and behold, the group of Immanuel Bloch and Stefan Kohr was the driving force in this study. Because they had a quantum microscope, because they could take a snapshot of the whole system, they could observe the fact that there was a string order in Mott insulator. So here is an image of their Mott insulator. Okay, this is a 2D plane, but then they do slices to ensure that this is... and they have the capability to measure site by site whether a site is occupied by a particle or is not occupied by a particle. So if you have this capability, you measure this thing, and then you repeat the measurement, and by repeating the measurement, you get the quantum average. But if you have one snapshot, you have the density at each site, which means you can compute the sine of the density, you can compute the hyperbolic tangent of the density, you can compute whatever you want. So you can measure these non-local order parameters. So in my opinion, I would say this capability that has been opened by quantum microscope to get a snapshot of a quantum problem and not just a local probe that tells you at one point I know what the object you measure is, has been one of the major contributions that cold atoms have brought in terms of new probes that really allow you to probe condensed matter. So, okay, if you want to know more about topological phase transition and so on, this editor had at the nose because they did this volume shortly before Kostelis and Taules got the Nobel Prize. So this was an interesting good summary of various developments on BKT phase transition. Okay. I'm left with, let's say, 20 minutes, so I wanted to tell you about another type of perturbation that you can put on a Latinger liquid, and this one is disorder. We discussed the periodic potential due to a lattice. Well, what about, I don't put a periodic potential, but I put dirt. Can we treat it? And the answer is yes, we can treat it by the same technology. And of course, when I put disorder on a 1D system, I know it will have very drastic effect. So here is my Hamiltonian, kinetic energy, interactions between the bosons, here written in first quantization, and then some disorder here, which will depend on which point I'm in. And this is a very old problem. We studied it together with Heinz Schulz in '87, so prehistoric, âge des cavernes. And again, this sounds like a formidable problem if you write it in the original boson language, because now you get a random potential which is coupled to the bosons. But if you use bosonization, it's actually not very different from the problem I wrote so far. It's very much like the Mott problem, except instead of getting a nice periodic function, you will get something which will be an integral over dx, a random variable, psi of x, times exponential of I 2 phi of x, plus Hermitian conjugate. If you have the periodic potential, this is just a number. If you have disorder, this is a random variable, and you need to average over this variable with, let's say, a distribution that will be, usually we like Gaussian and correlated disorder, so this will be something. So I'll pass on the way one solves this problem, and I will just give you the answer. And the answer is very interesting. Again, 1D behaves in a very interesting way. You know that if you have free particles, any amount of disorder in 1D gives you localization. It transforms the plane waves that exist for free particles into exponentially decreasing propagating waves. This is a celebrated Anderson localization, which is now let's say 60 years old, 60 plus years old. And for non-interacting particle, this is beaten to death. We know everything there is to know about this. For interacting particles, this is a huge challenge. What happens if we have both interactions and disorder? After all, interactions create superfluidity. A superfluid is resistant to disorder. By definition, it flows even when there is impurity. But on the other hand, if I put impurities but no interaction, I get exponentially localized. So I cannot have superfluidity. So how is this competition going? You see, the two hate each other. And so the question is, what happens? And so what happens in 1D, you can study by Tomonaga-Luttinger liquid theory. You have the non-interacting bosons, which are very special, and I don't want to discuss them. They are localized by rare events, by improbable configurations, because if one boson is localized, they all go there. Yeah. With fermions, it doesn't work. With fermions, only one fermion can go in a rare configuration. So the bosons which are non-interacting, they all go trapped in a finite region of space. But this explodes as soon as you put interaction. And now what you find is that there is a kind of dome here where the system is superfluid. So it's robust to disorder. So this is the disorder axis. This is the interaction axis. And you find, therefore, if you want, that interactions first delocalize the problem. This is what we would expect. An interaction is helping the system to be superfluid. It's making the superfluid robust. So it should kill the disorder. Yeah, but then if you continue, then this is the opposite. The interaction will make the system relocalize, and the system here is again something which is very much like an Anderson insulator localized by the disorder. So you get this weird phase diagram. So this superfluid phase is the normal Tomonaga-Luttinger liquid, and the localized phase has been nicknamed Bose glass. The word glass here is to be taken with a very loose sense. It's not, nobody tested for the glassy properties of this phase, but essentially, it's disordered, so why not call it a glass? Voilà. So this is the phase diagram that one gets. And again, you can study this by the same technology. So as an exercise, if you have time this afternoon and it's raining, just try to see how you can solve this problem and determine this phase diagram as it is determined now. So how to test this in cold atoms? People have a hard time putting a true disorder for various reasons. There are some groups, like the group of Alain Aspect, Vincent Josse, who did put real disorder from a speckle, but a simpler version is to put a quasi-periodic potential, which is the superposition of two incommensurate wave vectors. So you could say, well, if it's incommensurate, then I get something which will be kind of random. Actually, this is not completely wrong. This model has a name. It's called the Aubry-André model when there is no interaction. And it has a localization transition for non-interacting bosons. And for the case of interaction, this is something one can study. Here is the numerical phase diagram that you see for this model. This is the strength of the interaction, and this is the strength of one of the components. So let's say V1 here, it's called V2, but V1. And you see that you get the superfluid. If you crank up too much the interaction, unfortunately here you're polluted by the Mott insulator phase. But if you crank up the second component of the harmonic potential, then you go to the Bose glass phase. So this is very much like a true disorder. Voilà. Just to flash you one experiment, and then I'll stop here. I want to show you that people tested this. Here is the experiment which were done in the group of the same Giovanni Modugno that you saw before in Florence, in the group of Massimo Inguscio. And essentially, you have creation by using lasers of many tubes, and these many tubes, in their direction, there is a quasi-periodic potential which is made by a pair of lasers, each one with its own wavelength, and then measurement of the phase diagram. And we helped a little bit with a theory. This is Guillaume Roux in LPTMS, and Thomas Bartel, who helped with the theory. Here is the experimental phase diagram. What is measured here is the width of the peak in N of K. So this is something which is supposed in the superfluid to diverge as a power law. So this is supposed to go as K to the power minus nu, because it's the Fourier transform of the single particle correlation, psi dagger. And this one is a power law with an exponent 1 over 2k. So the broader this peak, the more the thing will be localized. You see that if you replace this by an exponential, this peak will become a potato. And you see that there are indeed a region here where the peak is narrow, and you have a region here where the peak is very broad, and this is in agreement with the phase diagram that you saw before. One can do more refined studies, but I don't want to discuss this, and let me skip a little bit the more refined questions. Maybe we'll discuss them next time as open problems for the system. So I'll leave you with this experimental phase diagram. There are many things we understand on this experimental phase diagram, but there are also many things we don't understand. So now we are entering slowly in the third lecture, which is no, not is nice and rosy in one dimension. We don't have the ultimate weapon which solves everything. And fortunately for you, because we need you, you know, to solve very difficult problems. We solved all the easy problems, we left you all the difficult ones. But there are very, very difficult problems, but I think rewarding problem that remains in one dimension, and we'll study those, we'll discuss some of those in the last lecture. And on that I stop, and I thank you for your attention.